Black holes don't die. Everyone knows that. Once something crosses the event horizon, it's gone forever, trapped in a gravitational prison so absolute that even light can't escape. These cosmic monsters just keep growing, devouring everything that comes near them, getting bigger and more massive throughout eternity. Except that's completely wrong. In 1974, a young physicist named Stephen Hawking discovered something that shocked the scientific world. Black holes aren't eternal. They're bleeding energy into space right now, slowly evaporating like puddles in the sun. Given enough time, every black hole in the universe will shrink down to nothing and explode in a final burst of radiation. The universe's most indestructible objects are actually dying. All of them. The question isn't whether black holes can die, it's how this is even possible. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. Let's start. Before Hawking's discovery, the physics was straightforward. A black hole forms when a massive star collapses, crushing all its matter into a point so dense that space-time curves back on itself. The boundary around this point, the event horizon, marks the point of no return. Cross that line and the geometry of space-time itself drags you toward the center. Not even traveling at light speed can save you, because space itself is falling inward faster than light can climb out. This led physicists to a simple conclusion. Black holes are one-way streets. Matter and energy go in, nothing comes out. They grow with every meal, and since the universe contains effectively infinite food in the form of gas, dust, and radiation, black holes should just keep growing forever. Some might merge with others, creating even larger black holes. But the total mass locked away behind event horizons should only increase. The universe seemed destined to eventually become a cold, dark place, dominated by ever-growing black holes. Then Hawking started thinking about quantum mechanics near the event horizon. Quantum field theory tells us that empty space isn't actually empty. The vacuum seethes with activity. Particle-antiparticle pairs constantly pop into existence, exist for the briefest instant, then annihilate each other. This happens everywhere, all the time, but it's normally invisible because these virtual particles disappear before they can affect anything. They're like quantum I owe us that get paid back immediately. Near a black hole's event horizon, something different happens. The intense curvature of space-time in this region can promote these virtual particles into real particles. One particle might fall into the black hole while its partner escapes into space. To a distant observer, it looks like the black hole is emitting particles. This is Hawking radiation, and it means black holes glow. Not much, though. A stellar mass black hole, the kind formed when a massive star collapses, has a temperature of about 62 billionths of a degree above absolute zero. That's far colder than the cosmic microwave background radiation filling space, which sits at 2.7 degrees above absolute zero. Right now, these black holes are actually gaining mass faster than they're losing it by absorbing background radiation. They're growing, not shrinking. But wait, billions upon billions of years. The universe continues expanding. The cosmic background radiation gets colder and more dilute, and eventually it will cool below the temperature of even massive black holes. When that happens, Hawking radiation will finally dominate. The black holes will start losing more energy than they gain. Here's where it gets strange. As a black hole radiates energy, it loses mass. Einstein taught us that mass and energy are equivalent, related by E equals mc squared. When energy leaves via Hawking radiation, the black hole's mass decreases. You'd expect this to make the black hole cool down, just like any normal object radiating heat. A hot piece of metal glows bright and gradually dims as it cools. Black holes do the exact opposite. The temperature of a black hole is inversely proportional to its mass. Smaller black holes are hotter than larger ones. As a black hole loses mass, its temperature rises. It radiates faster. It loses mass more quickly, which makes it hotter still. This creates a runaway process that accelerates throughout the black hole's life. For most of its existence, the evaporation is impossibly slow, but in the final stages, the black hole's temperature skyrockets and the evaporation becomes explosive. A solar mass black hole will take about 10 to the 67th years to evaporate completely. That's a 1 followed by 67 zeros. The universe is currently only about 14 billion years old, which is roughly 10 to the 10th years. The black hole's lifetime is longer than the current age of the universe, by a factor so large it breaks our ability to comprehend it. If you could watch a solar mass black hole evaporate, you'd spend essentially all of that time seeing nothing happen. The black hole would sit there, appearing completely static, for timescales that dwarf the current age of the universe by factors we don't have words for. Then, in the final fraction of a second, everything changes. The black hole, now shrunk to microscopic size, reaches temperatures of trillions of degrees or more. It radiates furiously, pumping vast amounts of energy into space. The final moments involve a violent explosion, a cosmic fireworks display that releases all the remaining mass energy in a burst of high-energy gamma rays. One moment there's a black hole. The next, there's only radiation spreading through space. No one has ever seen this happen. The timescales are too long. Any black holes small enough to be evaporating right now would have to be primordial black holes, tiny black holes that formed in the extremely early universe rather than from stellar collapse. These would need to have started with masses around 1 trillion kilograms to be exploding today. That might sound like a lot, but it's about the mass of a small mountain, vastly smaller than any black hole that could form from a collapsing star. Scientists have searched for the gamma ray bursts that would signal these explosions. They haven't found any confirmed detections. This doesn't mean primordial black holes don't exist, just that if they do exist, there aren't many of them, or they don't have the right masses to be exploding in the present era. The search continues, because finding even one would confirm Hawking's prediction directly. The physics behind Hawking radiation connects some of the deepest ideas in modern physics. Black holes sit at the intersection of general relativity, which describes gravity and space-time, and quantum mechanics, which describes the behavior of particles and fields. These two theories are the twin pillars of 20th century physics, but they don't play well together. They use different mathematical languages and different conceptual frameworks. Finding places where both theories matter simultaneously is crucial for developing a unified theory of quantum gravity. Oh, black holes are precisely such places. The event horizon is large-scale geometry described by general relativity, but the particle creation process involves quantum fields. Hawking's calculation required treating quantum fields in the curved spacetime of general relativity, a synthesis that revealed unexpected connections between black hole physics and thermodynamics. In 1971, Hawking proved the area theorem, which states that the total area of black hole event horizons never decreases. When black holes merge, the area of the final event horizon is always greater than or equal to the sum of the areas of the original black holes. This sounded suspiciously like the second law of thermodynamics, which says entropy never decreases in a closed system. Jacob Bekenstein suggested that this might not be a coincidence. Perhaps black holes actually have entropy proportional to their surface area. Hawking initially resisted this idea. If black holes have entropy, they must have temperature. And if they have temperature, they must radiate. But black holes don't radiate. They're black. That's what makes them black holes. Hawking set out to prove Bekenstein wrong by carefully calculating what would happen to quantum fields near a black hole's event horizon. Instead, he ended up proving Bekenstein right. Black holes do have temperature, they do radiate, and they do have entropy. The Bekenstein-Hawking entropy formula relates a black hole's entropy to the area of its event horizon. This was so important to Hawking that he reportedly said he wanted the formula engraved on his tombstone. It represents a deep connection between gravity, quantum mechanics, thermodynamics, and information theory. The formula reveals that black holes contain enormous amounts of entropy, far more than any other object of comparable mass. A solar mass black hole has entropy about 10 to the 54th times larger than the Sun itself. This entropy connection raises profound questions. In thermodynamics, entropy measures disorder, or more precisely, the number of microscopic states consistent with a given macroscopic state. For ordinary matter, we understand this microscopically. The entropy of a gas comes from all the possible positions and velocities of its molecules. But what are the microscopic states of a black hole? General relativity describes black holes as smooth geometric objects with no internal structure. A black hole is completely characterized by just three numbers: its mass, charge, and angular momentum. Where does all that entropy come from? This question has driven much of the research in quantum gravity over the past 50 years. String theory, loop quantum gravity, and other approaches have attempted to provide microscopic descriptions of black holes that could account for their entropy. String theory has had some success with certain special types of black holes, showing that the entropy can be counted by enumerating quantum states of strings and branes. But a complete understanding remains elusive. The discovery of Hawking radiation also created one of the biggest puzzles in theoretical physics: the black hole information paradox. Quantum mechanics says information cannot be destroyed. If you know the current state of a quantum system and the laws of physics, you can in principle reconstruct any past state or predict any future state. The evolution is deterministic and reversible, at least in principle. This property is called unitarity. But Hawking radiation appears to be thermal, meaning it's random. The radiation coming out of a black hole doesn't depend on what went in. If you throw an encyclopedia into a black hole and let the black hole evaporate completely, the radiation that emerges looks exactly like it would if you'd thrown in an equivalent mass of hydrogen gas or sand or anything else. The information about the encyclopedia's contents seems to be destroyed. This violates quantum mechanics' fundamental requirement that information must be preserved. Hawking initially argued that information really is destroyed in black hole evaporation, that this represents a breakdown of quantum mechanics in the presence of gravity. Most physicists found this unacceptable. Destroying information would undermine the foundations of quantum theory, creating logical paradoxes and making the universe fundamentally unpredictable. The debate raged for decades. Recent developments suggest that information is actually preserved, though the mechanism remains controversial. The key insight involves understanding how quantum entanglement behaves in curved space-time. The radiation coming out of a black hole isn't truly independent of what went in. It's entangled with the black hole's interior in subtle ways. As the black hole evaporates, these quantum correlations encode the information about what fell in. The information isn't destroyed, it's scrambled almost beyond recognition and spread across the radiation in incredibly complex patterns. This resolution connects to ideas about the holographic principle, which suggests that all the information about a volume of space can be encoded on its boundary surface. For black holes, this means all the information about the interior is somehow encoded on the two-dimensional event horizon. The three-dimensional interior is in some sense illusory, a hologram projected from information stored on the surface. These ideas point toward a radical reconception of space-time itself. Perhaps space isn't fundamental, but emerges from more basic quantum information. Perhaps the geometry of space-time is a large-scale approximation that breaks down at small scales, replaced by something more like a quantum computer processing information. Black hole evaporation would then be the process by which this quantum information, temporarily organized into geometric spacetime, gets released back into its fundamental form. The discovery that black holes can die transformed them from eternal prisons into dynamic, evolving objects with finite lifespans. It revealed unexpected connections between gravity, quantum mechanics, and thermodynamics. It created puzzles that have driven theoretical physics research for 50 years and continued to challenge our understanding. But Hawking radiation itself remains undetected. The effect is so weak for any black hole, we might actually observe that confirming it through direct measurement seems impossible with current technology. The black holes we can study are all far too cold, their Hawking radiation utterly drowned out by other sources. The only hope for direct detection would be finding a primordial black hole small enough to be hot, and none have been found. Yet in 2023, researchers discovered something that might change everything. The conventional picture of Hawking radiation places particle creation right at the event horizon, where the curvature of space-time is most extreme. But new calculations suggest that particles can also be created far beyond the horizon, where the curvature is much gentler. This means objects without event horizons might also evaporate. Neutron stars, white dwarfs, even planets. Anything with mass curves space-time around it, and that curvature might be enough to generate radiation through quantum effects. Not the dramatic Hawking radiation emerging from event horizons, but something subtler, spread across larger distances. The implications are staggering. If this holds up, the entire universe is slowly evaporating. Not just black holes waiting in the distant future to fade away, but everything with mass right now, losing energy through quantum processes so gradual, they're essentially invisible. Your body, this planet, every star, all leaking energy into the void at rates so infinitesimally small, they might as well be zero. Yet over timescales that dwarf even black hole evaporation, this universal decay could dominate. The researchers at Radboud University, who discovered this, combined techniques from physics, astronomy, and mathematics to investigate whether particle creation could occur far from event horizons. Their calculations suggest it can. Space-time curvature alone, without any horizon boundary, generates quantum radiation. The process differs from classic Hawking radiation, but produces similar results. Mass converts to energy, objects lose mass, and given enough time, everything decays. This changes what we thought about mortality on cosmic scales. Black holes were supposed to be the last object standing, outliving everything else, before finally evaporating in the deep future. Now it appears they're just the most dramatic example of a universal principle. Everything dies. Some deaths just take longer than others. But let's return to the black holes themselves, because their deaths remain the most spectacular. The timescales involved are so vast, they challenge comprehension. A black hole with the sun's mass would take roughly 10 to the 67th years to evaporate completely. That number doesn't register intuitively. The universe is currently about 13.8 billion years old. A solar mass black hole would take 10,000 trillion times longer than the current age of the universe to disappear. Supermassive black holes fare even worse, if worse is the right word. A black hole weighing 100 million solar masses, like the one at the center of our galaxy, would require something like 10 to the 100th years to evaporate. That's a 1, followed by 100 zeros. The current age of the universe is merely 10 to the 10th years. These timescales are so extreme that the numbers become abstract, losing connection to anything we can visualize or compare. Why so long? The temperature paradox provides the answer. Black holes don't cool as they lose mass. They heat up. A solar mass black hole has a temperature of about 62 nanokelvins. That's 62 billionths of a degree above absolute zero. It's far colder than the cosmic microwave background radiation filling space, which sits at 2.7 Kelvin. This creates a bizarre situation. Stellar mass black holes are actually gaining mass right now by absorbing background radiation, not losing it through Hawking radiation. The background is warmer than they are, so energy flows inward, not outward, only once the universe expands and cools enough for the background radiation to drop below a black hole's Hawking temperature will evaporation begin in earnest. for solar mass black holes. That won't happen for trillions of years. The universe needs to become colder than the black hole before the black hole can radiate more energy than it absorbs. Until then, these objects are essentially immortal, growing slowly as they feed on ambient radiation and occasional matter. Supermassive black holes are even colder. The largest black holes in the universe have temperatures measured in picokelvins, trillionths of a degree above absolute zero. They're the coldest natural objects in existence, colder than any laboratory has ever achieved. These frozen giants will persist long after every star has burned out, long after galaxies have dispersed into isolated stars wandering through expanding darkness, long after even those scattered stars have decayed into radiation or collapsed into more black holes. Eventually, though, even supermassive black holes will face their reckoning. The universe will expand and cool. The background radiation will thin and weaken, and one by one, starting with the smallest first, black holes will begin their long death march. The process accelerates as it progresses because of that temperature paradox. As a black hole loses mass, it gets hotter. Higher temperature means faster radiation. Faster radiation means more rapid mass loss. More mass loss means higher temperature still. The feedback loop becomes a runaway process. For most of a black hole's existence, nothing appears to happen. The evaporation is so gradual, it's effectively frozen in time. But in the final stages, everything changes. When a black hole has shrunk to roughly the mass of a mountain, its temperature starts climbing into ranges we'd recognize as hot. The radiation accelerates. The black hole glows brighter and brighter as it shrinks faster and faster. In the final moments, the temperature reaches billions or trillions of degrees. The black hole shines with impossible intensity, pouring out energy in every direction. Then it explodes. The last fraction of a second sees all remaining mass convert to energy in a cataclysmic burst of gamma rays and exotic particles. It's not a gentle fade, but a cosmic firework, a final defiant flash before the black hole winks out of existence forever. The explosion would be visible across vast distances, a beacon announcing that another black hole has finished its journey from formation to oblivion. We've never seen one of these explosions, not yet. The timescales are too long for any astrophysical black hole to have reached this stage. But there's a loophole: primordial black holes. Hypothetical objects that might have formed in the universe's first moments could be small enough to evaporate today. In the chaotic conditions right after the Big Bang, density fluctuations could have compressed regions of space into black holes before matter had time to disperse. Unlike stellar black holes, which can't be smaller than a few solar masses, because that's what stellar collapse produces, primordial black holes could theoretically have any mass. Some might have been microscopic, weighing as much as a mountain, but smaller than an atom. These tiny black holes would be incredibly hot and would evaporate quickly by cosmic standards. Hawking calculated that any primordial black hole with an initial mass less than about 10 to the 12th kilograms, roughly the mass of a large mountain, would have completely evaporated by now. Black holes with masses around this critical value would be finishing their evaporation today, producing those spectacular gamma ray bursts as they die. Astronomers have searched for these signals. Satellites scan the sky for unexplained gamma ray flashes that match the predicted signature of exploding primordial black holes. So far, nothing definitive has turned up. The absence of these bursts tells us something. Either primordial black holes don't exist in large numbers, or they're distributed differently than some theories predict, or our calculations are missing something. Each non-detection narrows the possibilities, constraining theories about the early universe and the nature of black holes themselves. The search continues because finding even one evaporating primordial black hole would revolutionize physics. It would confirm Hawking radiation directly, validate quantum effects in curved space-time, and prove that black holes really do die. But here's the frustrating reality. We're unlikely to ever detect Hawking radiation from astrophysical black holes directly. The effect is simply too weak. A stellar mass black hole radiates with a power output of about 10 to the negative 28th watts. That's 0.000000000000000000000000001 watts. For comparison, a typical LED light bulb uses about 1 watt. The black hole emits less than a trillionth of that. Detecting such faint radiation from objects light years away is effectively impossible with current or foreseeable technology. The situation worsens for larger black holes. A supermassive black hole radiates even less power because its temperature is lower. The radiation is so weak and so thoroughly drowned out by other sources — cosmic microwave background, starlight, interstellar gas — that separating the signal from the noise becomes hopeless. We can calculate that Hawking radiation exists. We can derive its properties mathematically, but we can't observe it directly from any black hole we're likely to encounter. This creates an odd situation where one of physics' most important theoretical predictions remains experimentally unverified. Hawking radiation is almost certainly real. The mathematics is solid. It connects multiple areas of physics consistently, and it resolves paradoxes that would otherwise break fundamental theories. But science traditionally requires experimental confirmation, and that confirmation may be permanently beyond our reach for astrophysical black holes. The 2023 discovery of radiation from space-time curvature beyond event horizons offers a potential path forward. If quantum effects generate radiation wherever space-time curves significantly, perhaps we can detect these effects in other contexts. Neutron stars have extremely curved space-time at their surfaces, but no event horizon. Could we detect quantum radiation from them? The signal would still be incredibly weak, but neutron stars are closer and more numerous than black holes. Maybe, with sufficiently sensitive instruments, we could catch the faint glow of quantum evaporation from these stellar remnants. Or perhaps we'll create microscopic black holes in particle accelerators. The Large Hadron Collider occasionally generates conditions of extreme energy density. Some theories predict that at high enough energies, tiny black holes might form and immediately evaporate, existing for only 10 to the negative 26 seconds before exploding in a shower of particles. These mini black holes, if they exist, would provide direct laboratory evidence for Hawking radiation. Detectors would observe the characteristic signature of quantum evaporation, a spherical burst of particles emerging from a point, carrying specific energy distributions that match theoretical predictions. So far, no such events have been detected. The energies required might be higher than we can achieve, or the theories predicting their formation might be wrong. But the search continues because the prize is so valuable. Laboratory confirmation of Hawking radiation would cement our understanding of quantum gravity and validate decades of theoretical work. The death of black holes matters beyond just understanding these exotic objects. It connects to the deepest questions about the universe's fate. What happens in the distant future when all stars have burned out, when galaxies have dispersed, when even matter itself has decayed? In the far future, black holes will dominate. They'll be the last remaining massive objects, slowly evaporating in an increasingly cold and empty universe. This era, called the black hole era by cosmologists, begins around 10 to the 40th years from now and extends to perhaps 10 to the 100th years or beyond. During this incomprehensibly long period, black holes are essentially the only game in town. They'll slowly merge, forming larger black holes. They'll continue accreting any matter that drifts too close, and all the while, they'll be evaporating, converting their mass back into radiation. Eventually, even the largest supermassive black holes will evaporate completely. The universe will enter what's called the dark era, where nothing exists but widely separated particles and photons, all moving away from each other as space continues expanding. Temperature approaches absolute zero. Entropy approaches maximum. Nothing changes anymore because there's nothing left to change. The universe reaches thermodynamic equilibrium, a state of maximum disorder and minimum information where no further events can occur. That's the current best guess for the universe's ultimate fate, assuming our understanding of physics is correct and nothing unexpected intervenes. Black holes represent the final chapter before the epilogue, the last dramatic events before eternal stillness. But that's assuming the universe itself doesn't have other plans. What if reality contains escape hatches we haven't discovered yet? What if the rules themselves can be rewritten? Here's where things get uncomfortable for physicists who prefer certainty. The universe might not play fair. Consider the simple fact that black holes can cheat death indefinitely. Feed them enough matter and they'll never evaporate. They just keep growing, resetting their evaporation clock every time they consume something. A supermassive black hole at a galaxy center sits surrounded by stars, gas clouds, occasional planets. It's like having an endless buffet. Every time it swallows material, it gains mass. More mass means lower temperature. Lower temperature means slower evaporation. The clock resets. This creates a strange possibility. If a black hole can continuously find fuel, it could survive the heat death of the universe itself, while everything else decays into radiation and approaches maximum entropy. An actively feeding black hole maintains structure, complexity, organization. It's an island of order in an ocean of disorder. But eventually, inevitably, the food runs out. Stars burn their fuel and die. Gas disperses. The universe expands, pushing everything farther apart. The distances between objects grow so vast that nothing can find anything else. The black hole finds itself alone in an increasingly empty cosmos. And that's when its doomsday clock finally starts ticking in earnest, unless something else intervenes first. The 2023 discovery from Radboud University suggests that space-time curvature alone generates radiation, independent of event horizons. This changes everything about how we think about evaporation. If ordinary massive objects can also radiate simply by curving space-time, then the entire universe is slowly bleeding energy. Neutron stars, white dwarfs, planets, even you and me, we're all technically evaporating, just at rates so stupidly slow they're meaningless on human timescales. But wait, if everything with mass curves spacetime, and curved spacetime produces radiation, then what happens to the radiation itself once it escapes? It carries energy. Energy has mass equivalence through Einstein's equation. So the radiation also curves spacetime. Does the radiation itself produce more radiation? This is where physicists start getting headaches. The research suggests that far beyond a black hole, space-time curvature still matters. The effect doesn't stop at the event horizon. It extends outward, weakening with distance, but never completely vanishing. This means quantum field theory and general relativity are dancing together in ways we're only beginning to understand. The marriage between these two theories has always been rocky. They speak different languages, operate on different principles, describe different scales. But here, in the context of black hole evaporation, they're forced to cooperate. And they're telling us something disturbing about the universe's future. If all massive objects evaporate through quantum effects in curved space-time, then matter itself is temporary, not just temporary on human scales or stellar scales, but fundamentally temporary, given enough time, 10 to the 100th years, 10 to the 200th years, numbers so large they're essentially meaningless. Everything dissolves. Every atom that ever existed will eventually decay into radiation. The universe becomes nothing but photons, and perhaps some exotic particles, all moving away from each other as space continues expanding. No structure, no complexity, no information, just maximum entropy and eternal expansion. This is bleaker than the traditional heat-death scenario. At least in the old version, matter persisted even if it was cold and dispersed. In this new picture, matter itself is transient. Black holes were supposed to be the last holdouts, the final bastions of structure before the universe reached its ultimate fate. Now we're learning. They're just slower at dying than everything else. But here's what keeps physicists awake at night. These calculations assume our current understanding of physics is correct. They assume quantum field theory and general relativity accurately describe reality at all scales and all times. They assume no new physics emerges as the universe ages. History suggests we should be cautious about such assumptions. Every time we've been confident we understood everything, nature has surprised us. Classical mechanics seemed complete until quantum mechanics revealed an entirely new layer of reality. Quantum mechanics seemed complete until quantum field theory showed particles aren't really particles. General relativity seemed to describe gravity perfectly until we discovered dark energy, which makes no sense in any existing framework. String theory was supposed to unify everything, but now we have multiple versions and no way to test them. The pattern is clear. Our theories work brilliantly within their domains, but reality is always more complex than we imagine. So when we extrapolate current physics forward 10 to the 100th years, we're making a truly audacious assumption that nothing fundamental changes over timescales millions of trillions of times longer than the universe's current age. Maybe something does change. Maybe at ultra-long timescales, vacuum decay becomes relevant. The vacuum of space might not be in its lowest energy state. It might be metastable, like a ball balanced on a hill, stable for now, but capable of rolling down to a lower state. If vacuum decay occurs, it would propagate at light speed, creating an expanding bubble of true vacuum with different physical constants. Everything in its path would be destroyed and reconstituted under new rules. Black holes might survive this transition, or they might not. The physics inside the bubble could be completely alien. Or maybe dark energy evolves. Current observations suggest dark energy has constant density. As space expands, more dark energy appears to fill it, maintaining constant density everywhere. But what if that's temporary? What if dark energy strengthens over time, eventually tearing apart galaxies, then stars, then atoms themselves in a Big Rip scenario? Or what if it weakens, allowing gravity to reassert itself and pull everything back together in a big crunch? Or maybe quantum gravity saves us. When space-time itself becomes quantum mechanical at the Planck scale, we genuinely don't know what happens. All our calculations break down. The mathematics produces infinities and nonsense. We need a complete theory of quantum gravity to understand the final moments of black hole evaporation, and we don't have one yet. String theory offers possibilities. Loop quantum gravity suggests alternatives. Other approaches propose different solutions. None are confirmed. This means the very end of a black hole's life, that final explosive burst when it reaches Planck mass, remains mysterious. Does it evaporate completely? Does it leave a remnant? Does it tunnel to another universe? Does it transform into something we haven't even conceived of? We're speculating in the dark. The information paradox compounds the uncertainty. If information cannot be destroyed and black holes evaporate completely, then where does the information go? The radiation must encode it somehow, but thermal radiation appears random. Recent work on quantum extremal surfaces and entanglement islands suggests information might be preserved through subtle quantum correlations, but the details remain contentious. Some physicists think the paradox indicates our understanding of space-time itself is wrong at fundamental levels. Maybe space-time is emergent rather than fundamental. Maybe it arises from more basic quantum information structures, like temperature emerges from molecular motion. If space-time itself isn't fundamental, then black holes aren't quite what we think they are. They might be complicated quantum information states that only appear to have event horizons and singularities in our approximate description. The true quantum reality could be completely different. This connects to the holographic principle, which suggests that all the information about a black hole's interior is encoded on its two-dimensional event horizon surface. Three-dimensional space might be a hologram projected from a lower dimensional boundary. If that's true, then asking what happens inside a black hole is like asking what happens inside a hologram. The question is based on a misunderstanding of what really exists. These ideas sound like science fiction, but they're serious physics proposals being actively researched at major universities. They're attempts to resolve genuine paradoxes and inconsistencies in our current theories. They're clues that our understanding remains incomplete, and that incompleteness matters tremendously when we try to predict the ultimate fate of black holes and the universe itself. Consider one more possibility that's rarely discussed. What if consciousness matters? Not in some mystical sense, but in the precise technical sense suggested by quantum mechanics. Observation affects quantum systems. Measurement collapses wave functions. The act of gathering information changes what's being observed. If black holes are quantum objects, and they must be at some level, then perhaps observation influences their behavior in ways we haven't considered. This isn't suggesting that thinking about black holes changes them. It's pointing to a deeper puzzle about the role of information and entropy in quantum systems. Black holes maximize entropy, but entropy is fundamentally about information, specifically missing information. The Bacon-Stein-Hawking entropy formula tells us how much information is hidden behind a black hole's event horizon. When that information escapes through Hawking radiation, something profound is happening about the relationship between physical systems and information itself. Maybe the universe doesn't end in maximum entropy. Maybe information itself generates structure. Maybe complexity is more fundamental than we realize, and the far future holds possibilities we can't currently imagine, because they depend on principles we haven't discovered. Or maybe none of this speculation matters. Maybe black holes really do just evaporate completely, leaving radiation. Maybe the universe really does reach maximum entropy and eternal expansion. Maybe the mathematics we have now accurately describes everything that will ever happen. Maybe reality is exactly as bleak as current physics suggests, but probably not. The history of physics teaches humility. Every generation thought they'd nearly figured everything out. Every generation was wrong, not because they were stupid, but because reality is deeper than any framework we construct to describe it. Our current theories are astonishingly successful within their domains, but those domains have boundaries. Beyond those boundaries lies territory we haven't mapped yet. Black holes sit at one of those boundaries. They're where quantum mechanics meets general relativity, where information theory meets thermodynamics, where our best physics starts producing paradoxes and contradictions. They're telling us we're missing something important. The question is whether we'll figure out what before we get distracted by easier problems that don't threaten our conceptual frameworks. The death of black holes matters because it connects to everything else. If we can understand how black holes evaporate completely, we'll understand quantum gravity. If we can solve the information paradox, we'll understand the relationship between quantum mechanics and space-time. If we can reconcile Hawking radiation with unitarity, we'll have taken a major step toward a complete theory of physics. And if we can't, we'll know our current theories are missing crucial pieces. The question isn't whether we'll solve these puzzles, it's when, and what solving them will reveal about the structure of reality itself. Start with something concrete. A black hole with the mass of our sun sits in empty space. No stars nearby, no gas to consume, no material to feed on, just the black hole and the vacuum of space. According to Hawking's calculations, this black hole will evaporate completely. But when? 10 to the 67th power years. That's the number physicists have settled on after decades of refining the mathematics. To put that in perspective, the universe is currently only about 14 billion years old. That's roughly 10 to the 10th power years. A solar mass black hole will take 10 to the 57th times the current age of the universe to evaporate. Your brain probably can't meaningfully process that number. Neither can mine. But here's another way to think about it. If you started counting seconds from the Big Bang until now, you'd have counted about 10 to the 18 seconds. To count to the lifetime of a solar mass black hole, you'd need to keep counting for so long that the original universe would have ended. New universes would have been born and died, and you still wouldn't be close to finished. These timescales reveal something crucial about Hawking radiation. For any black hole we can actually observe, anything formed from stellar collapse or grown through accretion, the evaporation process is so slow, it's essentially irrelevant to the current universe. A stellar mass black hole emits Hawking radiation at a temperature of 62 nanokelvins. The cosmic microwave background radiation that fills all of space has a temperature of 2.7 Kelvin. That's about 43 million times hotter than the Hawking radiation. This creates a paradox of sorts. Every black hole in the universe is technically evaporating through Hawking radiation, but every black hole is also absorbing energy from the cosmic microwave background. For any astrophysical black hole, anything massive enough to have formed in the real universe, the absorption vastly outweighs the emission. These black holes are growing, not shrinking. They're eating the leftover heat from the Big Bang faster than they're bleeding energy through quantum effects. Only when the universe expands and cools significantly further will this balance shift. Eventually, the cosmic microwave background will redshift to such low temperatures that even stellar mass black holes will emit more than they absorb. But that won't happen for an unimaginably long time. The universe would need to expand by factors we can barely write down before the background radiation becomes cooler than the Hawking temperature of a solar mass black hole. But what about smaller black holes? This is where things get interesting. Hawking radiation temperature is inversely proportional to mass. The smaller the black hole, the hotter it gets. A black hole with the mass of the Moon would have a Hawking temperature of about 3 Kelvin, slightly warmer than the cosmic microwave background. It would actually be losing mass right now, though very slowly. Make the black hole smaller still, and the temperature skyrockets. A black hole with the mass of Mount Everest would glow at room temperature. One with the mass of a large building would be hot enough to vaporize anything nearby. And a microscopic black hole the size of a proton would be radiating at temperatures high enough to dwarf the core of the hottest stars. The problem is that no known astrophysical process can create black holes this small. Stellar collapse requires at least a few solar masses of material. When a massive star explodes in a supernova and its core collapses, the resulting black hole has a minimum mass of several times our Sun. You simply can't make a moon mass black hole through stellar evolution, much less anything smaller. This is where primordial black holes enter the picture. In the first fraction of a second after the Big Bang, the universe was so dense that even small fluctuations in density could have collapsed to form black holes. These wouldn't be constrained by stellar evolution. They could theoretically have any mass, from microscopic to supermassive. And if primordial black holes formed with masses around 10 to the 12th kilograms, about the mass of a small mountain, they would be completing their evaporation right now. Think about what that means. Somewhere in the universe, possibly in the empty space between galaxies, tiny black holes that formed in the first instant of creation might be exploding in bursts of gamma rays. These would be the final death throes of objects that have been slowly evaporating for the entire history of the cosmos. They would have been radiating since before galaxies formed, before stars ignited, before atoms existed, and now, after nearly 14 billion years, they're reaching their final moments. Astronomers have searched for these explosions. Gamma-ray telescopes scan the sky looking for the characteristic signature of an evaporating primordial black hole. The final burst should be distinctive, a sudden flash of high-energy radiation appearing in random locations, lasting only a fraction of a second. So far, nothing has been found. No confirmed detections, no unambiguous signals. This absence tells us something important. Either primordial black holes with these masses don't exist, or they're much rarer than some theories predicted. The lack of detection places constraints on the conditions in the early universe. It tells us something about the density fluctuations in the first moments after the Big Bang. It's an example of how the search for black hole death connects to cosmology and the study of the universe's earliest moments. But let's imagine we did detect one. What would we learn? First, we'd have direct confirmation that Hawking radiation is real. Despite all the theoretical confidence, we've never actually observed it. Detecting the final burst from an evaporating primordial black hole would be the first experimental verification of one of the most important predictions in theoretical physics. It would confirm that black holes really do evaporate, that quantum effects really do operate near event horizons, that our understanding of these exotic objects is on the right track. Second, we'd learn about the physics at extreme energy scales. The final moments of black hole evaporation involve temperatures and energies far beyond what we can create in particle accelerators. The Large Hadron Collider can smash protons together at energies of a few trillion electron volts. An evaporating primordial black hole would be radiating at energies potentially millions or billions of times higher. Studying that radiation would give us a window into physics we can't access any other way. Third, we might get clues about quantum gravity. As a black hole shrinks down to the Planck mass, about 22 micrograms, the smooth space-time description of general relativity breaks down. The quantum nature of space-time itself becomes important. We don't have a complete theory of quantum gravity. String theory, loop quantum gravity, and other approaches offer different perspectives. but none have been experimentally verified. The final moments of black hole evaporation might provide the first empirical data about how space-time behaves at the Planck scale. But here's the fundamental challenge. The black holes we can observe, the ones formed from stellar collapse, the supermassive ones at galaxy centers, won't evaporate for timescales that make the current age of the universe look like an eye blink. And the black holes that might be evaporating now, if they exist at all, are too rare or too distant for us to detect with current technology. We're left with a theoretical prediction that seems extremely solid mathematically, but remains experimentally unverified. This isn't unusual in physics. General relativity predicted gravitational waves in 1916, but we didn't detect them until 2015. The Higgs boson was theorized in the 1960s, but not discovered until 2012. Sometimes the gap between prediction and confirmation spans generations. Hawking radiation might be one of those cases where the experimental verification comes long after the theoretical prediction, if it comes at all. Yet the implications of Hawking radiation extend far beyond black holes themselves. Remember the 2023 study showing that radiation can be generated by space-time curvature alone, even far from event horizons. If that's correct, then everything with mass is slowly evaporating through a similar process. Neutron stars, white dwarfs, planets, even ordinary matter. The timescales would be even longer than black hole evaporation, so long that they're essentially infinite by any practical measure. But the principle remains. Given enough time, everything decays. This connects to one of the deepest questions in cosmology. What is the ultimate fate of the universe? Current observations suggest the universe will expand forever, driven by dark energy. Galaxies will drift apart. Stars will burn out. Eventually, the universe will be cold, dark, and nearly empty. This scenario is called the Big Freeze, or heat death. It's the endgame predicted by thermodynamics, a state of maximum entropy where nothing interesting can happen anymore. In that far future, black holes would be the last remaining massive objects. They would persist long after stars have died, long after galaxies have dispersed, long after even the longest-lived stellar remnants have cooled to match the background temperature. The era of black holes would span timescales that dwarf the current age of the universe by factors we can barely comprehend. During this era, the largest black holes would gradually absorb matter and grow. Some could reach masses of 10 to the 14th solar masses, 100 trillion times the mass of our Sun, through the slow accumulation of whatever material remains. But even these monsters must eventually evaporate. The largest black holes would take roughly 2 times 10 to the 106th power years to completely evaporate. That number has 1 million zeros after the 2. It's so large that if you wrote out all those zeros, they wouldn't fit in this script. They wouldn't fit in a book. They might not even fit in a library. It's a timescale that makes forever seem like a reasonable approximation, yet it's not forever. Given enough time, enough of those unimaginable eons, even the largest black holes will evaporate completely. And when the last black hole finally disappears in its final burst of radiation, the universe will have entered its final era. What comes after that? is speculation built on speculation. Some theories suggest the universe continues its cold expansion indefinitely, with nothing but diffuse radiation and possibly stable particles like electrons and positrons scattered through an ever larger volume of space. Other theories propose stranger possibilities. Maybe the vacuum itself is unstable, and given enough time, it will decay to a lower energy state, fundamentally changing the laws of physics throughout the universe. Maybe quantum tunneling events become relevant on these ultra-long timescales, allowing impossible things to occasionally happen. Maybe the concept of time itself becomes meaningless in a universe with no remaining structure or complexity. But those are questions for a different discussion. For now, the key point is this: black hole evaporation isn't just an exotic prediction about distant objects. It's a window into the ultimate fate of everything. It connects quantum mechanics to thermodynamics to cosmology. It reveals tensions between our best theories that we haven't resolved. And it points toward a future so distant and strange that our current physics may not adequately describe it. The death of black holes matters because it forces us to confront the limits of our understanding. When we calculate what happens as a black hole shrinks to the Planck scale, our equations start producing infinities and contradictions. When we ask whether information is preserved during evaporation, we get different answers depending on which principles we prioritize. When we try to reconcile Hawking radiation with quantum mechanics, we discover paradoxes that have driven decades of research without clear resolution. These aren't just academic puzzles. They're signals that something important is missing from our theoretical framework, and finding that missing piece would represent one of the most significant advances in fundamental physics since quantum mechanics and relativity were first developed. So what happens when we probe those limits? When we push our theories to the edge of the Planck scale and ask what actually occurs in those final moments? The answer reveals cracks in the foundation of modern physics. At the heart of the problem sits quantum gravity, a theory we desperately need but don't actually have. General relativity describes gravity beautifully at large scales. Quantum mechanics governs the microscopic world with stunning precision. But when you try to combine them, when you need both theories working together in the same framework, the mathematics starts producing nonsense. Infinities appear where they shouldn't. Predictions become ambiguous. The equations that work perfectly in their separate domains suddenly conflict with each other. Black hole evaporation forces these two pillars of physics into direct confrontation. And right now, neither theory is willing to compromise. Consider what happens as a black hole shrinks. Throughout most of its lifetime, general relativity provides an excellent description. The space-time curvature is smooth and well-behaved. Hawking radiation can be calculated using semi-classical methods, essentially treating the quantum fields on the curved space-time background provided by general relativity. This approximation works beautifully for large black holes, but as the black hole loses mass and approaches the Planck scale, roughly 22 micrograms, about the mass of a grain of sand, everything changes. At these scales, quantum effects in the gravitational field itself become important. Space-time can no longer be treated as a smooth, classical background. It becomes quantum mechanical. subject to the same uncertainty and fluctuations that govern particles. We simply don't know how to describe that regime mathematically. String theory offers one possible framework. In string theory, the fundamental constituents of reality aren't point particles, but tiny vibrating strings. These strings naturally incorporate both quantum mechanics and gravity, potentially resolving the conflict. String theorists have made remarkable progress understanding black holes through this lens, showing how black hole entropy can be counted microscopically, and even suggesting that black holes might have complex internal structure, sometimes called fuzzballs, rather than being the smooth, featureless objects described by classical general relativity. Loop quantum gravity takes a different approach, proposing that space-time itself is quantized, made up of discrete units rather than being continuous. In this framework, the singularity at the center of a black hole might be replaced by a quantum bounce, potentially connecting our universe to another region of space-time through what's called a Planck star. Other approaches exist too. Each offers tantalizing hints about what might happen at the Planck scale, but none has been experimentally confirmed. We have ideas, mathematical frameworks, and suggestive calculations. What we lack is definitive evidence that any particular approach correctly describes nature. This uncertainty matters profoundly for black hole death. The very final moments when the black hole has shrunk to Planck dimensions and is about to release its last burst of energy occur precisely in the regime where our theories break down. We can calculate with reasonable confidence what happens up to that point. But the ultimate fate, whether the black hole evaporates completely or leaves behind a stable remnant, what form that final explosion takes, those questions remain open. Here's what makes this particularly frustrating. Unlike many quantum gravity questions that involve unobservable phenomena at impossible to reach energy scales, black hole evaporation should eventually produce observable effects. If primordial black holes exist with the right masses, they should be exploding right now, producing detectable gamma-ray bursts. We're looking for those signals. So far, we haven't found them, which tells us something about the population of primordial black holes, but leaves the theoretical questions unanswered. The timescales involved present another challenge. Even if we perfectly understood the physics, we couldn't watch a stellar mass black hole evaporate, not in a human lifetime, not in the lifetime of our species, not in 1 trillion times the current age of the universe. The process is simply too slow for anything we'll ever build to observe directly. So we're left with theory, mathematics, and indirect evidence. And that theory keeps pointing us toward deep problems. Take the information paradox. When Hawking first calculated that black holes emit thermal radiation, he concluded that information must be destroyed in the process. A black hole's radiation depends only on its mass, charge, and spin, not on the specific details of what fell in. If you throw an encyclopedia into a black hole and wait for it to evaporate, you get random thermal radiation out. The information about the encyclopedia's contents seems to have vanished from the universe. This directly contradicts quantum mechanics, which insists that information is never truly destroyed. In quantum theory, if you know the state of a system at one time and you know the laws of physics, you can in principle calculate its state at any other time. The evolution is unitary, reversible, and information preserving. One of these principles must be wrong. Either quantum mechanics breaks down for black holes, or general relativity's description of black holes is incomplete, or our understanding of how information works in quantum gravity is fundamentally flawed. For decades, physicists argued about which principle to abandon. Hawking initially insisted information was truly lost, suggesting quantum mechanics might need modification. Others argued the opposite, that general relativity must break down in ways that preserve information. The debate grew heated, with careers and reputations staked on different positions. Recent developments have shifted the consensus. Most physicists now believe information is preserved, though exactly how remains debated. The key insight came from applying ideas from string theory and the quantum field theory to calculate something called the Page curve, a prediction for how the entropy of Hawking radiation should evolve if information is truly preserved. Initially, as a black hole radiates, the entropy of that radiation increases. More radiation means more randomness. But at a critical point, roughly when the black hole has evaporated to half its original mass, the curve must turn over if information is conserved. The radiation must start becoming less random, more correlated, as it encodes information about the black hole's interior. By the time evaporation completes, the total entropy should match what you started with. For years, calculations couldn't reproduce this curve. They showed entropy increasing monotonically, suggesting information loss. But recently, incorporating subtle quantum effects and using techniques from holography, the idea that information in a volume of space can be encoded on its boundary, physicists have successfully calculated the Page curve. The mathematics now suggests information is preserved. But here's what's unsettling about this resolution. The calculations work. The math produces the right answer. Yet we still don't have a clear physical picture of how information escapes from a black hole. Is it encoded in subtle correlations in the radiation that our simple calculations miss? Does it escape through quantum effects near the horizon that we haven't properly accounted for? Is the black hole's interior somehow accessible from the outside in ways we don't understand? The equations suggest information gets out. The mechanism remains mysterious, and that mystery points towards something deeper. The information paradox isn't really about black holes specifically. It's about the relationship between quantum mechanics and space-time itself. It's about whether space and time are truly fundamental, or whether they emerge from something more basic. It's about the nature of reality at the deepest level. Black holes are just the arena where these questions become unavoidable. Consider another puzzle that emerges from black hole thermodynamics. Hawking showed that black holes have temperature and entropy. The entropy is proportional to the area of the event horizon, not the volume, but the surface area. This is strange. For ordinary objects, entropy typically scales with volume. A larger box can hold more gas molecules and thus has more entropy. But black holes are different. All their entropy lives on the boundary. This observation led to the holographic principle, the idea that the information content of any region of space might be encoded on its boundary, like a hologram encoding three-dimensional information on a two-dimensional surface. If true, this suggests something profound about the nature of space itself. Maybe the three dimensions we move through aren't truly fundamental. Maybe they're emergent, arising from information encoded on a lower dimensional boundary. Maybe space-time is a hologram. These ideas have driven decades of theoretical research. They've connected quantum mechanics to gravity in unexpected ways. They've suggested that space and time might not be the fundamental building blocks of reality, but rather emergent properties that arise from something more basic. And it all traces back to black holes slowly evaporating through Hawking radiation. But we still don't have a complete theory. We have pieces, beautiful mathematical structures that fit together in suggestive ways. We have the ADS/CFT correspondence, a precise mathematical relationship between gravity in certain spacetimes and quantum field theories without gravity. We have the Bekenstein-Hawking entropy formula, relating geometry to thermodynamics. We have string theory calculations that reproduce black hole properties from microscopic counting. We have the Page curve emerging from quantum extremal surfaces. What we lack is the full picture, a complete theory of quantum gravity that describes black holes from formation through evaporation with mathematical rigor and physical clarity, a framework that resolves the information paradox, not through clever calculations, but through clear understanding, a description of what happens at the Planck scale that we can test experimentally. These gaps matter because black hole evaporation sits at the intersection of everything we don't understand about fundamental physics. It involves quantum mechanics, general relativity, thermodynamics, and information theory all at once. It probes energy scales we can't reach in laboratories and timescales we can't observe directly. It asks questions about the nature of space, time, and information that our current theories can't fully answer. Every calculation we do, every theoretical framework we develop, eventually leads back to the same conclusion. We're missing something fundamental, some key insight that would make everything click into place. Maybe it's a new principle we haven't discovered yet. Maybe it's a mathematical structure we haven't invented. Maybe it's a way of thinking about physics that requires abandoning assumptions we've held for centuries. Whatever it is, black holes are pointing us toward it. Their death, slow, inevitable, and governed by laws we only partially understand, serves as a cosmic laboratory for testing our deepest theories. And right now, those theories are telling us they're incomplete. The universe seems determined to keep some secrets, at least for now. The question isn't whether we're missing something, it's what we're missing. Consider the timeline. Hawking published his radiation theory in 1974. We're now half a century past that breakthrough, armed with quantum field theory, string theory, gravitational wave detectors, and computational power Hawking could only dream about. We've confirmed his area theorem through direct observation of merging black holes. We've reproduced the Page curve using quantum extremal surfaces. We've built mathematical frameworks connecting black hole entropy to microscopic states. Yet we still can't tell you with certainty what happens in the final second of a black hole's death. The problem concentrates at a scale called the Planck length, roughly 10 to the power of minus 35 meters. This isn't just small, it's 20 orders of magnitude smaller than a proton. At this scale, quantum effects and gravitational effects become equally important. The smooth fabric of space-time that Einstein described starts to look less like a fabric and more like, well, we don't know. Foam, discrete chunks, something we lack the concepts to describe. When a black hole shrinks to about 22 micrograms, the Planck mass, its radius approaches 2 Planck lengths. At this point, its de Broglie wavelength equals its Schwarzschild radius. That's the moment when quantum mechanics and general relativity stop playing nice and start screaming at each other. Our equations break down. Infinities appear where they shouldn't. The smooth predictions of classical physics dissolve into quantum uncertainty. This is where a complete theory of quantum gravity becomes essential rather than optional. String theory offers one picture. In this framework, black holes aren't the smooth objects general relativity describes. They're fuzzballs, complicated tangles of vibrating strings that only appear smooth from a distance. The information about what fell into the black hole isn't lost inside an inaccessible interior. It's encoded in the complex quantum state of the fuzzball itself. When the black hole evaporates, that information can, in principle, escape with the radiation. Loop quantum gravity suggests something different. Here, space-time has a discrete structure at the Planck scale. It comes in chunks, like pixels on a screen. The black hole's interior might connect to a new region of space-time through a quantum bounce, similar to what might have preceded the Big Bang. The singularity isn't a point of infinite density, but a bridge to another space. These aren't just competing mathematical frameworks. They're fundamentally different visions of what space and time are. And here's what keeps physicists awake at night. We might not be able to test these ideas directly, ever. The energies required to probe the Planck scale are about 10 to the power of 19 times higher than what the Large Hadron Collider can achieve. Building a particle accelerator powerful enough would require more energy than exists in the observable universe. Creating a microscopic black hole in a laboratory, small enough that we could watch it evaporate in real time, needs collision energies we simply cannot reach. This leaves us hunting for indirect evidence. Primordial black holes offer one possibility. Unlike stellar mass black holes that form from collapsing stars, primordial black holes could have formed in the first fractions of a second after the Big Bang. Density fluctuations in the early universe might have been large enough that some regions collapsed directly into black holes. These could have any mass, from microscopic to supermassive. The critical mass is about 10 to the power of 12 kilograms. Any primordial black hole smaller than this would have completely evaporated by now through Hawking radiation. One with exactly this mass would be exploding right now in the final throes of its death, releasing a burst of gamma rays visible across cosmic distances. We've searched for these bursts. Gamma-ray telescopes have scanned the sky for the characteristic signature of an evaporating black hole. The final explosion should be distinctive, a specific energy spectrum, a specific time profile. It would be unmistakable. We haven't found any. This non-detection tells us something important. Either primordial black holes with these masses don't exist, or they're far rarer than some theories predicted. Each year we don't detect, an evaporation burst tightens the constraints on how many small primordial black holes could be out there. But absence of evidence isn't evidence of absence. Maybe primordial black holes exist, but have different masses. Maybe their final explosions look different than we calculated. Maybe there's something wrong with our understanding of Hawking radiation itself. That last possibility brings us to 2023, when researchers at Radboud University published something unexpected. They showed that Hawking radiation might not require an event horizon at all. The intense curvature of space-time around any massive object, not just black holes, could generate radiation through quantum effects. Neutron stars might be slowly evaporating. White dwarfs, even planets, though at rates so slow, they're meaningless on any practical timescale. This radiation doesn't come from virtual particles at a boundary. It emerges from the interaction between quantum fields and curved spacetime, far beyond where any event horizon would be. If this holds up, it fundamentally changes how we think about Hawking's discovery. It means evaporation isn't a property of black holes specifically. It's a property of space-time curvature itself. Anything with mass warps space-time. That warping allows quantum fields to produce real particles. Those particles carry energy away. Given enough time, truly staggering amounts of time, everything in the universe would eventually evaporate. Stars will die first. The smallest red dwarfs might burn for 10 trillion years, but eventually all fusion will cease. White dwarfs will cool to black dwarfs. Neutron stars will radiate away their heat. Dead stellar remnants will float through the expanding darkness. Galaxies will evaporate next, not through radiation, but through gravitational interactions that occasionally fling stars into intergalactic space. Over 10 to the power of 19 years, galaxies will slowly dissipate. After 10 to the power of 20 years, even galaxy clusters will have dispersed. Then come the black holes. They'll be the last massive objects remaining, growing slowly through occasional collisions, but primarily just existing in the void. For solar mass black holes, this era lasts 10 to the power of 67 years. Supermassive black holes at galactic centers take 10 to the power of 100 years or longer. These numbers mock comprehension. Write out 10 to the power of 100, and you get a 1 followed by 100 zeros. The universe has existed for only 10 to the power of 10 years. You'd need to live through the current age of the universe 10 billion trillion 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 times to witness a supermassive black hole evaporate. Some black holes might grow even larger as superclusters of galaxies collapse over truly cosmic timescales. They could form black holes of 10 to the power of 14 solar masses. These would take 2 times 10 to the power of 106 years to evaporate, a 1 with 106 zeros. But the math is clear. Eventually, inevitably, they all die. The universe runs a one-way program. Entropy increases. Structure dissolves. Complexity gives way to simplicity. Unless something unexpected happens at the Planck scale. Maybe black holes don't evaporate completely. Maybe they leave remnants, stable objects at the Planck mass that persist forever, each carrying the information about everything that fell in. the universe could eventually fill with these remnants, a sea of Planck mass particles encoding the entire history of cosmic structure. Or maybe information leaks out faster than we think through subtle correlations in the Hawking radiation. Recent calculations using quantum extremal surfaces suggest this might work mathematically. The radiation could be far more correlated than simple thermal analysis indicates. The Page curve, that graph of entropy evolution that serves as the litmus test for information preservation, now emerges naturally from these calculations. After decades of getting the wrong answer, of seeing entropy increase monotonically in ways that violated quantum mechanics, we can finally reproduce the curve's distinctive shape. Entropy rises as radiation accumulates, peaks around the halfway point, then falls as the remaining radiation becomes increasingly correlated. This is progress. Real, concrete progress toward resolving the information paradox. But it's progress in mathematical consistency, not physical understanding. We can make the numbers work. We can satisfy the requirements of quantum mechanics. What we can't do is point to a physical mechanism and say, here, this is how information actually escapes. The holographic principle offers tantalizing hints. If all the information inside a black hole is encoded on its two-dimensional surface, then maybe evaporation is really just the slow reading out of that surface information. The three-dimensional interior might be an illusion, a holographic projection from the boundary. This idea has proven remarkably fertile. The ADS/CFT correspondence provides a precise mathematical realization of holography in certain spacetimes. In these spaces, a gravitational theory in the bulk is exactly equivalent to a quantum field theory without gravity on the boundary. Black holes in the bulk correspond to thermal states in the boundary theory. Information that seems lost in the bulk is manifestly preserved in the boundary theory. But our universe isn't ADS space. The correspondence works in spacetimes with negative cosmological constant, and we live in one with positive cosmological constant. The dark energy pushing cosmic expansion. Translating these insights to our actual universe remains an open problem. Every solution creates new questions. Every answer reveals deeper mysteries. This is what theoretical physics looks like at the frontier. Not steady accumulation of facts, but cycles of confusion and clarity, each revolution exposing how much we don't understand. Black holes force this confrontation. They sit at the intersection of our three great theories: quantum mechanics, general relativity, thermodynamics, and refuse to let them coexist peacefully. Something has to give. Some assumption we've held about the nature of space, time, or information must be wrong. Finding out which assumption is the challenge. Without experiments, without observations that can distinguish between competing theories, we're left with mathematical consistency as our guide. We follow the equations wherever they lead, trusting that nature rewards mathematical elegance. Sometimes this works spectacularly. Einstein predicted gravitational waves from pure theory in 1916. We detected them a century later, exactly as described. Hawking predicted black hole radiation from pure theory in 1974. We still haven't detected it, but every indirect test supports his framework. Other times, mathematics leads us astray. String theory is mathematically beautiful, but makes no testable predictions we can currently verify. Loop quantum gravity solves certain problems, but introduces new ones. Competing approaches multiply faster than we can evaluate them. This is where black hole evaporation becomes crucial. It's not just another theoretical puzzle. It's the puzzle, the place where all our uncertainties concentrate. When the mathematics fails to provide definitive answers, we look to experiments. And here's where black hole physics becomes almost cruelly frustrating. We can't observe Hawking radiation from astrophysical black holes. The temperature is too low. A stellar mass black hole radiates at 62 nanokelvins, far colder than the cosmic microwave background at 2.7 Kelvin. These black holes are actually growing, not shrinking, absorbing more energy from the ambient radiation bath than they emit. For supermassive black holes, the situation is even more hopeless. Their temperatures drop to billionths of a Kelvin. Detecting their Hawking radiation would be like trying to hear a whisper in a hurricane. The signal is buried beneath countless other sources of radiation, completely inaccessible to our instruments. So we wait. We search for primordial black holes, hypothetical objects that might have formed in the early universe with masses small enough to be evaporating now. Hawking calculated that any black hole with initial mass less than about 10 to the power of 12 kilograms would have completely evaporated by today. These primordial black holes, if they exist, would be dying right now. Their final moments would produce spectacular bursts of gamma rays, cosmic fireworks announcing the death of objects that have existed since the first fraction of a second after the Big Bang. Gamma ray telescopes scan the sky constantly. They detect bursts from all kinds of astrophysical sources, colliding neutron stars, supernovae, active galactic nuclei. But none of these signals match the expected signature of an evaporating black hole. Does this mean primordial black holes don't exist? Not necessarily. It constrains how many there could be, sets upper limits on their population density. But absence of evidence isn't evidence of absence. The universe is vast. Our instruments are limited. A primordial black hole could evaporate in some remote corner of the cosmos, and we'd never know. This is what makes black hole evaporation different from most physics. Usually, we can test theories, build experiments, measure outcomes, confirm or refute predictions. But the timescales here stretch beyond imagination. A solar mass black hole evaporates in 10 to the power of 67 years. The universe is only 10 to the power of 10 years old. We'd need to wait 10 to the power of 57 times the current age of the universe to watch one die. For supermassive black holes, the numbers become absurd, 10 to the power of 100 years or longer. By the time these objects begin their death throes, the universe will be unrecognizable. All stars will have burned out, galaxies will have dispersed, even protons might have decayed if certain theories are correct. The cosmos will be a cold, dark expanse where black holes are the last remaining massive objects. Cosmologists call this the black hole era. It's one of the final chapters in the universe's history, beginning roughly 10 to the power of 40 years from now and lasting until around 10 to the power of 100 years. During this epoch, black holes dominate the mass budget. Everything else has either decayed, dispersed, or been consumed. Then comes the dark era. After the last black holes evaporate, only radiation remains. Photons and neutrinos and whatever other stable particles exist, all redshifted to infinitesimal energies by cosmic expansion. The universe becomes a diffuse gas approaching absolute zero, with density approaching zero, expanding forever. This is the ultimate heat death, maximum entropy, thermal equilibrium. No free energy available to do work. No structure, no complexity, no possibility for life or consciousness or anything interesting. Just endless expansion into infinite darkness. Unless something changes. Unless the cosmological constant isn't constant. Unless dark energy evolves. Unless quantum effects at cosmic scales introduce new physics. We're extrapolating trillions upon trillions of years into the future based on current observations spanning mere decades. But assuming our understanding holds, black hole evaporation determines the timeline of cosmic death. The rate at which these objects radiate sets the clock for the universe's final transformation. Here's what makes this profound. Black holes themselves are temporary. They seem permanent. Nothing escapes. They grow by consuming matter. They appear eternal. Yet quantum mechanics ensures they're mortal. Every black hole in existence is bleeding energy into space, slowly but inexorably approaching its own demise. The smallest die first. Hypothetical micro-black holes, if they exist, would evaporate almost instantly in bursts of radiation. Stellar mass black holes take 10 to the power of 67 years. Supermassive black holes take 10 to the power of 100 years or more. But they all die eventually. This creates a strange inversion. Black holes are the ultimate cosmic destroyers. They consume stars, they shred planets, they trap light itself. Yet they're also victims of their own existence, sentenced to slow dissolution by the quantum nature of reality. And the mechanism is counterintuitive. As a black hole loses mass, it doesn't cool down like normal objects. It heats up. The temperature rises. This creates a runaway effect. The hotter it gets, the faster it radiates, which makes it lose mass more quickly, which makes it even hotter. For most of a black hole's lifetime, this process is glacially slow. A solar mass black hole loses about 10 to the power of minus 28 watts of power through Hawking radiation. That's approximately 1 photon every few thousand years. The mass decrease is utterly negligible, but in the final stages, everything accelerates. When a black hole has shrunk to planetary mass, it's radiating at the power of a small star. At lunar mass, it's brighter than the sun. At mountain mass, it's a cosmic searchlight. At human mass, it's exploding. The very last moment is spectacular. All remaining energy escapes at once in a violent burst of gamma rays and exotic particles. The temperature reaches trillions of degrees. The black hole doesn't fade gently. It detonates. If you could somehow observe this from a safe distance, you'd see the black hole shrink rapidly, glowing brighter and brighter, its temperature climbing exponentially. Then, in a fraction of a second, it would disappear in a flash of radiation that would outshine entire galaxies. This hasn't been observed because no astrophysical black holes are anywhere near this stage. They're all still in the imperceptibly slow phase that will last for epochs beyond comprehension. But the physics is clear. The equations are unambiguous. Every black hole is destined for this explosive finale. What happens at the very end remains uncertain. Does the black hole evaporate completely, leaving only radiation? Or does it leave behind a remnant, some stable Planck mass object that persists forever? The question matters because it connects to information preservation. If evaporation goes to completion, then all the information that fell into the black hole must have escaped somehow in the radiation. But if a remnant persists, maybe that remnant carries the missing information. Remnants solve certain problems while creating others. They preserve information, which satisfies quantum mechanics. But they're strange objects, Planck-scale black holes with enormous entropy packed into impossibly small volumes. And if remnants are stable, the universe should be full of them, remnants from every black hole that's ever evaporated. We don't see these remnants. No observations suggest they exist. But we're looking at a universe that's only 10 to the power of 10 years old, and black hole evaporation doesn't become relevant until 10 to the power of 40 years or later. Remnants from primordial black holes might exist, but finding them would be extraordinarily difficult. So we're left extrapolating from theory, taking equations that work beautifully in testable regimes and extending them to energy scales we can never directly probe, trusting that the mathematics remains valid across 60 orders of magnitude in energy. Sometimes this trust is rewarded. General relativity predicted black holes decades before we observed them. Quantum mechanics predicted the Higgs boson decades before CERN detected it. The equations guided us to discoveries we couldn't have made through observation alone. Other times, extrapolation fails. Classical physics worked perfectly for centuries until quantum mechanics revealed its limits. Quantum field theory works beautifully until you probe the Planck scale, where it breaks down. Every theory has boundaries beyond which new physics emerges. Black hole evaporation sits right at this boundary. It requires quantum field theory in curved spacetime, a regime we can't test experimentally. It involves energies and timescales far beyond our reach. We're navigating by pure mathematics, hoping the map matches the territory. Recent developments offer some reassurance. A 2023 study showed that Hawking radiation might not require an event horizon at all. Space-time curvature alone, even far from any horizon, can generate particle creation. This suggests the phenomenon is more robust than originally thought, less dependent on specific black hole properties. The implications are staggering. If curvature alone produces radiation, then everything with mass is slowly evaporating. Neutron stars, white dwarfs, planets, even ordinary matter. The timescales are absurdly long, far longer than black hole evaporation. But the principle holds. Given enough time, everything decays. This extends the heat death prediction even further. Not only will black holes evaporate, but all matter will eventually dissolve into radiation through quantum gravitational effects. The universe's ultimate fate is radiation. Photons and neutrinos spreading thinner and thinner as space expands forever. But this far future physics remains speculative. We're making predictions about events 100 years from now, based on observations spanning decades. The uncertainty is immense. New physics could emerge. Our understanding could be incomplete. What we know for certain is that black holes aren't eternal. They radiate, they lose mass, they die. This much is established through multiple theoretical frameworks and indirect observational tests. The area theorem has been confirmed through gravitational wave observations. The thermodynamic properties are mathematically rigorous. The details, exactly how information escapes, whether remnants exist, what happens at the Planck scale, remain debated. But the broad picture is clear. Black holes are temporary features in an evolving universe, destined to evaporate through quantum processes that connect gravity to thermodynamics in profound ways. Understanding black hole death forces us to confront the limits of knowledge itself. Some questions may be answerable only through mathematics, never through experiment. Some predictions may be testable only by civilizations far more advanced than ours, if any survive to those distant epochs. This is theoretical physics at its most speculative and most rigorous, extrapolating from solid foundations into unknown territory, guided by mathematical consistency and physical intuition. We follow the equations because we have nothing else. And sometimes, astonishingly, the equations turn out to be right. The mathematics, however beautiful, might be leading us astray in ways we can't yet recognize. Consider how confident Newton was about absolute space and time. His equations worked perfectly. They predicted planetary orbits with stunning accuracy. Every observation confirmed his framework. Then Einstein showed that the entire conceptual foundation was wrong. Space and time weren't separate, absolute entities, but aspects of a unified, flexible space-time. What if we're making a similar mistake with black hole evaporation? The calculations assume space-time remains smooth down to the Planck scale. They assume quantum field theory remains valid at energies we can never test. They assume information conservation holds in regimes where neither quantum mechanics nor general relativity alone applies. These aren't small assumptions. They're fundamental leaps of faith disguised as mathematical rigor. String theory offers hints that space-time itself might be emergent rather than fundamental. Loop quantum gravity suggests space-time has discrete structure at the smallest scales. Both frameworks modify how we think about black hole horizons and evaporation. Neither has been experimentally verified. We're extrapolating equations across 60 orders of magnitude in energy, from the weak Hawking radiation we can calculate to the final Planck scale explosion we can barely describe. That's like using Newtonian mechanics, which works perfectly for throwing baseballs, to predict what happens when you approach light speed. The equations don't tell you when they've exceeded their domain of validity. Here's what keeps physicists awake at night. Every fundamental theory we've discovered has turned out to be an approximation. Newtonian mechanics approximates relativistic mechanics at low speeds. Classical physics approximates quantum mechanics at large scales. Even our best current theories, quantum field theory and general relativity, are known to be incomplete because they contradict each other at extreme scales. Black hole evaporation lives precisely at this intersection where our theories fail. The 2023 discovery that curvature alone, without an event horizon, can produce radiation seemed to vindicate Hawking's ideas. If you don't need a horizon, the phenomenon is more robust, less dependent on uncertain quantum gravity effects near the event horizon. Problem solved, right? Not quite. This discovery actually deepens the mystery. If everything with mass produces this radiation, not just black holes, then ordinary matter is fundamentally unstable over sufficiently long timescales. Your coffee cup is evaporating. The Earth is evaporating. Every atom in your body is slowly, imperceptibly decaying through quantum gravitational effects. The timescales are absurd, longer than any black hole evaporation time. But the principle stands. All matter has finite lifetime. This prediction emerges from the same mathematical framework that gives us Hawking radiation. If we trust one, we must accept the other. Both rely on quantum field theory in curved spacetime, a framework that's never been experimentally tested. Think about that. We're predicting the ultimate fate of all matter based on calculations we cannot verify. The observational confirmation of Hawking's area theorem using gravitational waves provided crucial validation. When two black holes merged to form a larger one, the final event horizon area exceeded the sum of the original areas, exactly as predicted. This wasn't a direct detection of Hawking radiation, but it confirmed that black holes obey thermodynamic laws in practice, not just in theory. Yet even this confirmation has limits. The area theorem works whether or not black holes actually evaporate. It describes what happens during mergers, not during the slow quantum decay we've been discussing. It validates the thermodynamic framework without proving the radiation mechanism itself. We're assembling a puzzle where most pieces fit together beautifully, but the final picture remains obscured by missing sections we can't access. The information paradox exemplifies this frustration. For decades after Hawking's 1974 discovery, physicists debated whether information could truly be destroyed. Quantum mechanics says no. Information must be conserved. But Hawking radiation appeared to be purely thermal, carrying no information about what fell into the black hole. Throw an encyclopedia into a black hole. Wait for it to evaporate. The radiation that emerges looks completely random, dependent only on the black hole's mass, charge, and spin. The encyclopedia's contents seem to have vanished from the universe entirely, violating quantum mechanics' fundamental principles. The paradox isn't just academic. It suggests either quantum mechanics or general relativity must be wrong at some fundamental level. Both can't be completely correct. Recent work on quantum extremal surfaces and the Page curve suggests information is preserved after all. The entropy of the radiation initially increases, but at the halfway point of evaporation, it begins decreasing. The final radiation state has the same entropy as the initial matter that formed the black hole. Information conserved, mathematically elegant, physically reassuring, completely unverifiable. The Page curve emerges from calculations involving quantum extremal surfaces, geometric structures in spacetime that determine how information flows. These calculations require assuming certain properties about quantum gravity, properties we can't test. Different assumptions yield different results. We choose the ones that preserve information because they seem more consistent with quantum mechanics. But that's an aesthetic choice, not an empirical one. What if nature doesn't care about our aesthetic preferences? The holographic principle offers another perspective. It suggests that all the information about a black hole's interior is encoded on its two-dimensional event horizon, like a hologram encoding three-dimensional images on a flat surface. This principle has been rigorously proven in certain theoretical frameworks, particularly in anti-de Sitter space using ADS/CFT duality. Our universe, however, isn't anti-de Sitter space. It's expanding with positive cosmological constant. The mathematical proofs don't directly apply to the black holes we actually observe. We're extrapolating again, hoping the principles remain valid when transplanted to different contexts. String theory suggests black holes might not be smooth, featureless objects, but instead have complex internal structure, fuzzballs that could encode information throughout their volume, rather than just on the horizon. This would resolve the information paradox elegantly. Information never falls past a true horizon, because no such horizon exists in quantum gravity. Except we don't know if string theory correctly describes nature. After decades of development, it remains experimentally unconfirmed. The fuzzball proposal is mathematically beautiful, but might be describing a reality that doesn't exist. Every proposed solution to the information paradox requires accepting frameworks that go beyond established physics. We're forced to choose between violating quantum mechanics, violating general relativity, or accepting speculative extensions of both. None of the options are satisfying. Meanwhile, the actual mechanism of information escape remains mysterious even if we accept that information is preserved. Does it leak out gradually in subtle correlations in the radiation? Does it burst out in the final explosion? Does the event horizon have structure we haven't detected? Nobody knows. The Planck scale looms over all these discussions, like an impenetrable wall. When a black hole has evaporated down to Planck mass, roughly 22 micrograms, our equations completely break down. The quantum uncertainty in the black hole's position becomes comparable to its Schwarzschild radius. Space-time itself becomes quantum. All our classical and semi-classical approximations fail simultaneously. What happens in those final moments? Complete evaporation? Stable remnant? Something else entirely? We have educated guesses, but no answers. Some physicists suggest Planck scale remnants could solve the information paradox. All the information gets compressed into a tiny, stable object that persists after the apparent evaporation. This preserves information and unitarity without requiring information to escape during the evaporation process. But Planck scale remnants create their own problems. If they're stable and contain arbitrary amounts of information, you could have infinite species of them, each encoding different information states. This leads to thermodynamic issues and violations of other principles. The cure might be worse than the disease. Others propose that the final explosion releases all the remaining information at once. The black hole doesn't evaporate completely smoothly, but undergoes a phase transition near the Planck scale, producing a distinctive signature. No such signature has been detected. but we wouldn't necessarily recognize it if we saw it. The primordial black hole searches offer the only realistic hope for observational evidence. Black holes formed in the early universe with masses around 10 to the power of 12 kilograms should be completing their evaporation now, producing gamma-ray bursts we could potentially detect. Decades of searching have found nothing. This null result constrains how many primordial black holes exist, but doesn't prove they don't exist. They might be rarer than we thought. Their final bursts might look different than predicted. Our detectors might not be sensitive enough to the right energy ranges. The absence of evidence isn't evidence of absence, especially when we're not entirely sure what we're looking for. The detection challenge goes deeper than technology. A stellar mass black hole has a Hawking temperature of 62 nanokelvins, far colder than the cosmic microwave background at 2.7 Kelvin. These black holes are actually growing, not shrinking, because they absorb more energy from background radiation than they emit. Every black hole in the current universe that formed through normal astrophysical processes is gaining mass, not losing it. Hawking radiation exists, but is overwhelmed by other effects. We're predicting a phenomenon that won't become observable for billions upon billions of years. By the time stellar black holes begin genuinely evaporating, the universe will be unimaginably different. All stars will have died. Galaxies will have dispersed. The cosmic microwave background will have redshifted to essentially zero temperature. Black holes will be the last remaining massive structures in a vast, cold, expanding emptiness. Only then does evaporation dominate over accretion. Only then does Hawking radiation become the primary process governing black hole evolution. And only then, 10 to the power of 60 years from now at minimum, could a sufficiently advanced civilization potentially observe black hole evaporation directly. We'll never see it happen. Neither will our descendants for countless generations. Neither will any civilization that arises in the next quadrillion years. The phenomenon we're describing with such mathematical precision occurs on timescales that dwarf all human experience and comprehension. This creates a peculiar epistemological situation. We're making detailed predictions about processes that will never be observed by anyone alive today, that might never be observed by any form of intelligence. Depending on the universe's long-term evolution, we're doing physics in a regime permanently beyond experimental verification. That doesn't make it wrong. General relativity predicted black holes decades before we observed them. Quantum mechanics predicted the Higgs boson decades before CERN detected it. Theory can guide us to truths we can't directly access, but it does make it uncertain in ways that conventional physics isn't. When you can't test predictions, you can't distinguish between correct extrapolations and beautiful mistakes. The universe might be telling us something profound through this inaccessibility. Perhaps there are fundamental limits to what can be known, not technological limits, but limits built into the structure of reality itself. Events beyond certain horizons, processes at certain energy scales, phenomena on certain timescales might be permanently beyond the reach of empirical investigation. If so, we're left with mathematics as our only guide. We follow the equations because we have nothing else. We trust their predictions because they've been reliable before. We hope that the patterns we've discovered continue to hold in regimes we can never directly explore. Sometimes this trust is rewarded. Sometimes the equations lead us to unexpected truths. But sometimes they lead us astray, revealing their limitations only when new physics emerges to replace them. Black hole evaporation sits at this uncertain boundary, where theory exceeds observation, where mathematics ventures beyond the empirical, where predictions become increasingly speculative, the further they extend into deep time. Respond to this message with read if you understand the context and instructions. Yet despite these uncertainties, the predictions remain remarkably precise. A 1 solar mass black hole will evaporate in 10 to the power of 67 years. Supermassive black holes stretch this to 10 to the power of 100 years or beyond. The largest black holes in existence, those that will form from collapsing galaxy superclusters, might persist for 2 times 10 to the power of 106 years. These aren't vague estimates. They're calculated from first principles using equations we trust. The mathematics speaks with confidence about events unimaginably distant in time. But here's what makes this genuinely strange. We're describing the death of objects that currently can't die. Every black hole in today's universe is growing, not shrinking. The cosmic microwave background bathes everything in 2.7 Kelvin radiation, far hotter than any stellar mass black hole's Hawking temperature. These objects absorb more energy from their surroundings than they emit. They're getting bigger, slowly, imperceptibly, but consistently bigger. Black hole evaporation isn't happening now. It won't happen for incomprehensible stretches of time. We're predicting a phenomenon that belongs to a universe radically different from ours, a universe where stars are ancient history, where galaxies have dissolved, where the cosmic microwave background has redshifted to near zero. Only in that distant era does Hawking radiation finally dominate. Only then do black holes genuinely begin to die. There's something almost absurd about this precision applied to such remoteness. We can calculate to incredible accuracy when something will happen that nobody will ever witness. We can describe in mathematical detail a process that occurs in conditions permanently beyond experimental reach. This creates a peculiar relationship with truth. Scientific knowledge typically grounds itself in observation. Theory predicts, experiment confirms, understanding deepens. But black hole evaporation occurs in a regime where this cycle can't complete. No one will observe a stellar mass black hole evaporate. No civilization will last the 10 to the 67th years required. No form of intelligence we can imagine will persist through timescales that dwarf the current age of the universe by factors of 10 to the power of 57. We're doing physics in permanent darkness, guided only by mathematical consistency and theoretical extrapolation. Sometimes this works beautifully. General relativity predicted gravitational waves a century before LIGO detected them. Quantum mechanics predicted antimatter before it showed up in cosmic rays. Theory can illuminate what observation hasn't yet revealed. But sometimes theory misleads. Perfectly consistent mathematics can describe universes that don't exist. Elegant equations can extend beyond their domain of validity, producing results that seem meaningful but aren't. How do we know which situation applies to black hole evaporation? We can't. Not definitively. Not without waiting timescales that exceed any meaningful concept of verification. This doesn't make the physics wrong. The logic is sound. The mathematics is rigorous. The theoretical framework combines general relativity and quantum field theory in ways that seem correct. Hawking's derivation has been checked and rechecked by generations of physicists, but it does make it uncertain in ways that differ from conventional physics. When you predict the orbit of Mars, you can verify by observation. When you predict nuclear decay rates, you can test in laboratories. When you predict black hole evaporation on timescales of 10 to the power of 67 years, you're beyond the reach of empirical confirmation. You're left trusting that the patterns you've discovered continue to hold in regimes you can't access, that the universe remains mathematically consistent even when nobody's watching, that the equations that work here and now still apply in the unimaginably distant future. Recent developments add unexpected complications. A 2023 study from Radboud University revealed that space-time curvature alone, independent of event horizons, can generate radiation. Objects without event horizons emit this radiation. Neutron stars, white dwarfs, even ordinary matter. If this holds, everything in the universe is slowly evaporating, not just black holes, everything. The timescales remain enormous. A neutron star won't evaporate for periods that make black hole lifetimes look brief. But the principle changes something fundamental. The universe isn't heading toward an endpoint where black holes are the last remaining objects, slowly radiating away. It's heading toward a state where all matter gradually dissolves. Nothing is permanent. Nothing is stable. Given sufficient time, all structure decays to radiation. This extends the reach of quantum gravity into unexpected territory. Previously, we thought these effects mattered only for black holes and the earliest moments after the Big Bang. Now, they appear relevant for all massive objects, just on timescales we'd previously considered infinite. The universe's ultimate fate shifts accordingly. Not a cold, dark expanse dotted with evaporating black holes, but a cold, dark expanse where everything, black holes, neutron stars, dead planets, even free protons, gradually decays through quantum gravitational processes. The mechanism differs from Hawking radiation in important ways. It's not tied to event horizons. It emerges from space-time curvature itself, from the quantum field excitations that curved geometry produces. But it achieves the same result: slow, inexorable conversion of mass to radiation. This raises questions that extend beyond physics into philosophy. If all matter eventually evaporates, what does that say about the nature of existence? If structure is temporary on cosmological timescales, does permanence mean anything? The atoms in your body will persist for periods that dwarf human timescales. They'll survive the death of the sun, the dissolution of the Milky Way, the fading of the last stars. But given 10 to the power of 100 years or more, even they might decay. Nothing is eternal. Not stars, not galaxies, not the atoms themselves. Everything is temporary structure emerging briefly from quantum fields, persisting for finite periods, eventually dissolving back to radiation. This perspective transforms how we think about the cosmos. The universe isn't building towards some stable end state. It's not creating permanent structures that will endure forever. It's more like a vast, slow river, constantly flowing, constantly changing, creating temporary patterns that persist for a while before dissolving. Black holes represent the most extreme version of this temporary existence. They're the last massive structures to form, the longest-lasting objects in the universe's inventory. But even they eventually succumb to quantum processes operating on timescales that dwarf all human comprehension. There's a kind of cosmic democracy in this. Nothing gets to persist indefinitely. The grandest structures in the universe, supermassive black holes weighing billions of suns, face the same ultimate fate as the smallest particles. They just take longer to get there. The final moments remain mysterious. When a black hole shrinks to near the Planck mass, roughly 22 micrograms, our theories break down. General relativity describes smooth spacetime, but at these scales, spacetime itself becomes quantum. The fabric of reality develops structure we can't yet calculate. Does the black hole evaporate completely? Does it leave a Planck-scale remnant? Does something unexpected emerge from quantum gravity? We genuinely don't know. String theory suggests possibilities. Loop quantum gravity offers different perspectives. Various approaches to quantum gravity make different predictions, but none have been tested. None can be tested in the regime where they matter most, the very last fraction of a second, when the black hole's temperature reaches trillions of degrees, when it explodes in a final burst of gamma rays, remains speculative. We can describe the approach to this moment with confidence. The moment itself eludes us. This represents one of the deepest frontiers in physics. The boundary where gravity meets quantum mechanics, where space-time itself becomes uncertain, where our most successful theories acknowledge their limitations. Solving this might require revolutionary insights, new mathematical frameworks, conceptual breakthroughs that reshape how we think about space, time, and matter. Or it might require something we can't yet imagine, a perspective so different from current physics that we lack the language to describe it. Black hole evaporation forces us to confront these questions. It pushes theory to extremes where observation can't follow, where mathematics ventures beyond the empirical, where predictions become increasingly speculative. Yet the questions persist. What happens when a black hole completely evaporates? Where does the information go? How does quantum gravity resolve the final moments? What remains when the last black hole dies? These aren't idle curiosities. They're fundamental questions about the nature of reality, about how the universe operates in regimes we can't access, about whether our theories correctly describe domains permanently beyond verification. The answers might reshape physics. They might reveal new principles governing quantum gravity. They might demonstrate that information is preserved in ways we haven't understood. Or they might show that our current framework is incomplete, that black hole evaporation exposes gaps requiring entirely new physics. We're left in a peculiar position. We can calculate with extraordinary precision when black holes will die. We can describe their temperature evolution, their radiation spectrum, their evaporation timescale. We can follow the mathematics from stellar collapse to final explosion. But we can't verify any of it through observation. We can't test whether our predictions hold in the regimes where they matter most. We can't confirm that black holes actually die the way our equations suggest. This might be the ultimate expression of theoretical physics, pure mathematics venturing into territories observation can't reach, making definite predictions about phenomena that might never be witnessed, trusting that the patterns we've discovered continue to hold in the unimaginably distant future. Sometimes this trust is warranted. Sometimes the equations lead us to truths we couldn't have discovered through observation alone. But sometimes they mislead, revealing their limitations only when new physics emerges to replace them. Black hole evaporation sits at this uncertain boundary. It's simultaneously our most confident prediction about the universe's ultimate fate and our most speculative extrapolation into permanently inaccessible regimes. The mathematics is beautiful. The physics is elegant. The predictions are precise. But the timescales are so vast, the energy so extreme, the phenomena so remote, that we're essentially describing a universe that doesn't exist yet and won't exist for periods that dwarf all human comprehension. In that distant future, 10 to the power of 67 years from now, or 10 to the power of 100, or 2 times 10 to the power of 106, the last black holes will indeed evaporate. They'll shrink, heat up, and explode in final bursts of radiation. The universe will transition from containing massive objects to containing only diffuse radiation, gradually cooling and expanding forever. This represents the end of structure, the final chapter in the story of matter. After black holes evaporate, nothing remains capable of significant gravitational influence. No stars, no planets, no black holes, just radiation, spreading ever thinner across expanding space. It's a quiet ending, not a dramatic collapse or a violent destruction, but a slow fade into cold, dark emptiness. The universe doesn't end with a bang. It doesn't even end with a whimper. It just gradually becomes less interesting, structure dissolving into homogeneity, complexity giving way to simplicity. Black holes are the last holdouts against this fate. They're the final islands of concentrated mass in an increasingly dilute cosmos. When they evaporate, they take with them the last remnants of the universe's structured phase. What comes after belongs to an era we can barely imagine, a universe vastly older than the current one, vastly emptier, vastly colder, a universe where the brief period when stars shone and galaxies formed is ancient history, separated from the present by timescales that dwarf the current cosmic age. And in that unimaginable future, the predictions we've made today about Hawking radiation, about black hole evaporation, about the slow death of the universe's last massive objects, will finally become reality. If the equations are right, if the extrapolations hold, if the universe continues to obey the patterns we've discovered in its youth. That's the profound uncertainty at the heart of black hole evaporation. We're making detailed predictions about a future so distant that verification becomes meaningless. We're describing the death of objects that won't die for timescales exceeding all human comprehension. The physics might be correct. The mathematics might perfectly describe reality. but we'll never know for certain. The universe keeps its deepest secrets on timescales that guarantee we can only speculate about the final chapter in the story of black holes. The mathematics tells us black holes die. The equations are precise, the logic rigorous, the theoretical framework tested across multiple domains. We can calculate evaporation times to extraordinary accuracy, 10 to the power of 67 years for stellar mass black holes, 10 to the power of 100 years for supermassive ones, even longer for the giants that will form from collapsing galaxy superclusters. But here's what makes this genuinely unsettling. We're describing phenomena that occur on timescales, rendering verification essentially meaningless. Not difficult, not challenging. Meaningless in any practical sense. Consider what 10 to the power of 67 years actually represents. The universe has existed for roughly 10 to the power of 10 years. You'd need to live through the current age of the universe 10 million trillion trillion times to witness a solar mass black hole evaporate. By the time these objects begin their death throes, the cosmos will bear no resemblance to anything we recognize. Every star will have burned out. Every galaxy will have dispersed. The cosmic microwave background will have redshifted to essentially zero. Black holes will be the last remaining massive structures, floating alone in a vast, cold, expanding darkness. And we're making detailed predictions about what happens in that unimaginable future, based on observations spanning mere decades and equations we can't test at the relevant energy scales. This represents theoretical physics at its most audacious and most uncertain. We're extrapolating current understanding across 60 orders of magnitude in energy, from the weak radiation we can calculate to the violent Planck-scale explosions we can barely describe. We're trusting that patterns discovered in accessible regimes continue to hold where no observation can ever reach. The 2023 discovery that space-time curvature alone generates radiation, independent of event horizons, adds another layer of strangeness. If true, everything with mass is slowly evaporating, not just black holes, neutron stars, white dwarfs, planets, even the atoms in your body, though on timescales so vast they might as well be infinite. All matter becomes temporary. All structure eventually dissolves. Given enough time, the universe transforms from containing objects to containing only diffuse radiation, gradually cooling and expanding forever. This isn't the dramatic ending we might expect. No cosmic crunch, no big rip, just slow, inexorable decay into maximum entropy and minimum complexity. The universe doesn't end. It just becomes progressively less interesting until nothing capable of change remains. Black holes mark the final chapter before this ultimate fate. They're the last massive objects, the longest lasting structures, the final islands of concentrated energy in an increasingly empty cosmos. When the last one evaporates, whenever that inconceivable moment arrives, the universe enters its final era. What happens in those ultimate moments remains genuinely uncertain. Does the black hole evaporate completely? Does it leave a Planck mass remnant? Does quantum gravity introduce phenomena we haven't imagined? We have educated guesses, competing frameworks, mathematical models that might or might not describe reality. The information paradox persists despite decades of effort. Recent work on quantum extremal surfaces reproduces the page curve, suggesting information is preserved. But the physical mechanism remains mysterious. How does information actually escape? Where does it hide during evaporation? Nobody knows for certain. String theory offers fuzzballs. Loop quantum gravity suggests bounces. Remnant proposals preserve information through stable Planck-scale objects. Each framework makes different predictions. None can be definitively tested. This creates a peculiar epistemological situation. We're doing physics in a regime permanently beyond experimental verification. Every prediction about black hole evaporation on cosmological timescales requires trusting that our current theories remain valid where they can never be checked. Sometimes this trust is warranted. General relativity predicted gravitational waves a century before detection. Quantum mechanics anticipated antimatter before discovery. Theory can illuminate what observation hasn't yet revealed. But sometimes, theory misleads. Perfectly consistent mathematics can describe universes that don't exist. Elegant equations can extend beyond their domain of validity, producing results that seem meaningful but aren't. How do we know which applies to black hole evaporation? We can't. Not with certainty. Not without waiting timescales exceeding any meaningful concept of verification. The area theorem has been confirmed through gravitational wave observations. Black holes really do obey thermodynamic laws. They really do have temperature and entropy. The mathematical framework connecting gravity to thermodynamics appears solid, but confirming the area theorem during mergers isn't the same as confirming Hawking radiation during evaporation. The first describes what happens when black holes combine. The second describes what happens when they slowly dissolve through quantum effects over unimaginable periods. We've never detected Hawking radiation, not from stellar mass black holes, which are too cold, not from supermassive black holes, which are even colder, not from primordial black holes, which might not exist or might be too rare to find. Every search for evaporating primordial black holes comes up empty. Every gamma-ray telescope scans the sky looking for the characteristic burst of a dying black hole. Nothing. Year after year, survey after survey, no confirmed detections. This absence doesn't prove the theory wrong. Primordial black holes might simply be rare. Their final explosions might look different than predicted. Our instruments might not have sufficient sensitivity, but it does mean the central prediction of Hawking's theory remains experimentally unverified 50 years after its proposal. We're left trusting mathematics, following equations into regimes where observation can't follow, hoping that the patterns we've discovered continue to hold in the unimaginably distant future. That might be enough. The logic is sound. The framework combines general relativity and quantum field theory in ways that seem correct. Generations of physicists have checked the calculations. The theory makes sense within our current understanding of physics, but current understanding has limits. Every previous theoretical framework eventually revealed boundaries beyond which new physics emerged. Newtonian mechanics gave way to relativity. Classical physics yielded to quantum mechanics. Our best current theories, quantum field theory and general relativity are known to be incomplete because they contradict each other at extreme scales. Black hole evaporation lives precisely at this intersection where theories fail. It requires quantum gravity, a framework we desperately need but don't actually have. String theory, loop quantum gravity, and other approaches offer possibilities. None have been confirmed. The very final moments when a black hole reaches Planck mass remain genuinely mysterious. The smooth space-time of general relativity breaks down. The quantum nature of space-time itself becomes important, and we simply don't know how to describe that regime with mathematical rigor. This represents one of the deepest frontiers in physics, the boundary where gravity meets quantum mechanics, where space-time becomes uncertain, where our most successful theories acknowledge their limitations. Solving this might require revolutionary insights comparable to relativity or quantum mechanics, new mathematical frameworks, conceptual breakthroughs that reshape how we think about space, time, and matter, or something we can't yet imagine, a perspective so different from current physics that we lack the language to describe it. Black holes are pointing us toward this missing piece. Their death, slow, inevitable, and governed by laws we only partially understand, serves as a cosmic laboratory for testing our deepest theories. And right now, those theories are telling us they're incomplete. We can calculate when black holes die. We can describe their temperature evolution, their radiation spectrum, their evaporation timeline. We can follow the mathematics from formation to final explosion with extraordinary precision, but we can't verify any of it through direct observation. We can't test whether predictions hold in the regimes where they matter most. We can't confirm that black holes actually die the way our equations suggest. This might be the ultimate expression of theoretical physics, pure mathematics venturing where observation can't reach, making definite predictions about phenomena that might never be witnessed, trusting that patterns discovered in accessible regimes continue to hold in the permanently inaccessible. The universe might keep these particular secrets forever, not because we lack sufficient technology or because we haven't been clever enough, but because the timescales involved transcend any meaningful concept of verification. By the time black holes begin genuinely evaporating, humanity will be ancient history. Our species will have evolved beyond recognition or gone extinct. The Earth will have been consumed by the dying sun. The Milky Way will have merged with Andromeda. Every star we can currently observe will have burned out. And still, the black holes will persist, slowly radiating, gradually shrinking, following the precise mathematical choreography that Hawking described decades ago. In 10 to the power of 67 years, or 10 to the power of 100, or 2 times 10 to the power of 106 years, they'll finally complete their journey from formation to oblivion. They'll heat up in those final stages, radiating faster and faster as they shrink, eventually exploding in bursts of gamma rays that nobody will be around to observe. The universe will transition from containing massive objects to containing only radiation. Structure will dissolve into homogeneity. Complexity will give way to simplicity. The cosmic story that began with quantum fluctuations in the Big Bang will end with quantum radiation from evaporating black holes. unless something unexpected intervenes, unless dark energy evolves, unless vacuum decay occurs, unless quantum gravity introduces phenomena we haven't anticipated, unless the universe has other plans we can't currently imagine. We're extrapolating current physics across timescales that dwarf the universe's current age by factors so large they lose connection to anything comprehensible. We're assuming nothing fundamental changes over periods millions of trillions of times longer than the entire history of cosmic evolution. That's a bold assumption, perhaps too bold. History teaches that reality is always more complex than our theories suggest. New physics emerges when we probe regimes sufficiently different from where our theories were developed. Black hole evaporation probes the most extreme regime imaginable, the intersection of quantum mechanics, general relativity, thermodynamics, and information theory, all operating on timescales and energy scales permanently beyond direct observation. The mathematics is beautiful, the physics is elegant, the predictions are precise. But beauty, elegance, and precision don't guarantee truth. They suggest we're on the right track. They indicate our theories capture important aspects of reality, but they don't prove we understand everything about black hole death. 50 years after Hawking's discovery, we've made remarkable progress. We've confirmed the area theorem. We've reproduced the Page curve. We've developed sophisticated frameworks connecting quantum mechanics to gravity. We've built mathematical structures that suggest information is preserved during evaporation. But we still haven't detected Hawking radiation. We still can't describe the final Planck scale moments. We still don't have a complete theory of quantum gravity. We're still extrapolating beyond what we can verify. The question isn't whether black holes can die. The equations say they must. The logic is compelling. The theoretical framework appears sound. Barring revolutionary changes to fundamental physics, black hole evaporation is almost certainly real. The question is whether we'll ever know for certain, whether any form of intelligence will persist long enough to witness these phenomena directly, whether the universe operates according to the patterns we've discovered or contains surprises that await us in regimes we can't yet access. Black holes challenge us to accept uncertainty at the deepest level, to make predictions we can't verify, to trust mathematics where observation fails, to extrapolate across timescales that render conventional scientific method essentially meaningless. This might be uncomfortable for a discipline that prides itself on empirical verification, but it might also represent the future of theoretical physics, increasingly precise predictions about increasingly remote phenomena, guided by mathematical consistency rather than experimental confirmation. We're learning to navigate by pure theory, following equations because we have nothing else, trusting that the universe remains logically consistent even when nobody's watching, accepting that some questions might be answerable only through mathematics, never through direct observation. Black hole evaporation exemplifies this shift. It's simultaneously our most confident prediction about the universe's ultimate fate and our most speculative extrapolation into permanently inaccessible regimes. The mathematics speaks with precision about events unimaginably distant in time. Whether those predictions describe reality remains genuinely uncertain. That uncertainty isn't failure. It's honesty about the limits of knowledge when confronting phenomena that transcend all scales of direct investigation. It's recognition that the universe might keep certain secrets forever, not because we're insufficiently clever, but because the timescales involved exceed any meaningful concept of verification. Black holes die. The mathematics is clear. Whether we'll ever know for certain belongs to a future so distant, it might as well be never. And maybe that's the most profound lesson these objects teach us, that some truths exist beyond the reach of observation, accessible only through the abstract beauty of mathematics and the hope that our equations correctly describe a reality we can never directly witness.